Hello, this is A squared at mathandstuff.com with a video that's an expansion of a talk on resources for teaching functions in developmental math, Precalc, and Calc 1. At mathandstuff.com, at the bottom of the home page is a link for mathandstuff.com on video. Between the company logo at the top and the video link on the bottom, there are a number of other links. Some of them we will be using. We will be using termtiles today. We will be using tokens and spreadsheets. We will be using exploring functions through the use of manipulatives. We will be using sketchpads. All those are available, but because it's a video, it's best linked down at the video logo at the bottom of the page. So I'm going to click that. On the video page, there's a whole section on digital manipulatives. There are other videos available. We're going to be using resources for teaching functions in developmental math, Precalc, and Calc 1. So I'm just going to click that link. Takes us to just below the slope song, which we'll look at also. Takes us to the link, which includes the video. Once I finish recording it, a local version of that, which you don't need, same thing, a PDF file of the web page and the web page itself. This is the content of the talk and of the video. We'll go over that now just by going to the web page. I'm clicking on the web page, and it's for a talk given September 29th, 2023 at Raritan Valley Community College. Here again is the abstract. We're focusing on digital manipulative spreadsheets, geometry sketchpads, on topics like the composition of functions, translations and reflections of functions, composition, inverse, trig functions of the form a function of bx minus c plus d, and so on. That's the abstract, but I'm pointing out that Geometry Sketchpad is now free, and all the materials you will see today in the video are free. So let's just begin. The overview or the rationale for doing all this movement is best seen perhaps in the link to math class languages. Here are the languages. Overreaching all of the languages is the mother tongue or other tongues. Many of my students are not primary English speakers. That English is their secondary language, and their mother tongue is more familiar to them, but may not have the math words that they need. So we address that issue. But mother tongue is at the same time the most sophisticated and the most basic. A circle means something in the real world, and it means the same thing but more in the STEM or math world. A mathematician who is versed only in formal spoken mathematics and formal, written, symbolic mathematics may not address the learner who is accustomed to doing things with their hands and not writing things down, just either working with their hands or seeing in a picture. And these are, I declare, and other experts agree, different forms of communication, different ways of approaching. I call them languages. The most sophisticated is the verbal and auditory. Nothing's written down. It's all spoken. It's all done mentally and verbally. Symbolic usually is written symbols, but maybe written words. And what makes it a little confusing sometimes is symbol speak. In other words, 3x plus 5 instead of 5 more than 3 times a number. Very, very different communication. Digital manipulative, we will be playing with today. Moving pictures is what this video is about. Static pictures, there are in the neighborhood of 17,000 web pages, spreadsheet, and images on this site. It's a lot you can play with. Concrete, there's nothing in the video that is concrete. It's all digital. That's the only way I can present it to you. But the website addresses the original version of the digital manipulative, the concrete manipulative. That's the big picture of why we're doing the talk, why I'm presenting things this way. I can go into more detail. I'm just going to link that, and we'll just look at a few things to think about. The golden rules. Discuss this with your partner. Is the most valuable strategy if you're dealing with a group situation. Discuss this with yourself. Is the most valuable strategy at any time. Other important ideas. Introduce in the concrete, the most basic. Debrief in the abstract, the most mental. Regularly require translation from one language to another. Do it in the verbal. Do it in the pictorial. Do it in the concrete if possible. Good stories are worth retelling. Tell a story in as many math languages as possible. Just a few more comments. All right, so you got the idea of why. Now I'm going to take you to the page that's probably the most radical. You can see how strange in a moment. We're going to go to here a slope. The agenda is introducing slope. I do it with a little bit of history and urban legend, and then go directly to the slope of 0. Listen. Well, it gets more interesting if you wish to listen to a slope of 1. And I'm sure you could expect what a slope of -1 should sound like. Is another thing that, in addition to video of this page and a PDF file of this page, there are 2 more things to look at. This one is called a slope meter, It was created, before 1989, believe it or not. And it's part of the material found in exploring functions through the use of manipulatives. We'll look at it in a moment. It's a slope meter. It measures slope. So you can take this, which comes on a transparency, and place it on function images, which you can move around. But I'd like to go to the video of this. So where do I find a video? I go to the video, or I go to the PDF, or what we're going to do now is we're going to a sketchpad. None of this is mentioned in the talk. The talk is only 45 minutes. Here we have it expanded. From René Descartes, who with Fermat is recognized as the creditors for co-discovering, developing analytic geometry. We take his urban legend about M for the use of slope. Descartes looked at the ceiling, mapped the movement of the fly, and we get the coordinate system Cartesian plane. Take Descartes, still lying in bed, look out the window, see mountains, and that's where the slope and M come from. So if you look at only one function, if you're over here looking out the window, and this is on your left, the hiker walks down the slope. If you're the hiker down here, you're looking at the hiker is at the bottom where there is no vertical incline. That's a slope of 0. The hiker here is going up the mountain. That's a positive slope. So we have, in just this parabola shown, we have a negative slope, a 0, and a positive slope. And all that might be is looking out the window at a mountain and a valley. The slope meter, I mentioned, was created for real concrete use. And I'm just going to put a point. Doesn't matter where I put it. Let's stick it there. I'm going to attempt to move. Well, that didn't work. I'm going to attempt to move the slope meter, the arm, and the point all over here. And if I fail, that's fine. All right, it all moved. I'm placing it right on the point. I now have the slope meter in position, and I can dial the arm. So here's the 0 slope we talked about out the window. These are positive slopes. These are negative slopes. Function-wise, a slope of 1 is a normal slope for most functions, but at this particular point, that's the slope of the parabola as close as I can get it using this arm. We go back to rise and run. Let's just go a little bit better here. I see this point as being on the curve. So the slope is rise, 1, 2, 3, 4, run, 1, 2, 3, 4, 5, 6. The slope of that point is 4/6 or 2/3. But the arm is what's giving us the ability. That is that here here. No, that's not quite the tangent. There we go. And estimate it by that. But that arm gives us the ability to look at the slope. Now, you can count the dots. That's the way you can, that's the only way you can do it if it's a concrete manipulative, but since it's digital, we can move the slope meter and just expose the arm. So slope is rise over run. And here we have the slope. Make it visible. Let's change the point. Let's move the arm. Let's move the arm. And you can see now it's a slope of negative 1.47. We also have available parabolas with a tangent ready to be moved, so you can look at the slope of the tangent, which is the slope of the curve. We have a cubic. You can see positive slope decreasing, 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 gets to 0 at the top of the hill, negative slope, 0 at the bottom of the hill, positive slope. That's for what are we on? We're on a cubic. Well, you can get fancy with your polynomials. You can edit your polynomial. Rational function. This is the closest I come to displaying what it means to have an infinite slope or have the slope undefined. So I can move the arm. You can see the slope of the tangent. It's still decreasing. It's still a negative slope. It's getting closer to 0. Closer to 0. That's about 0, rounding it. I'm now going up, 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 up. It's getting steeper. Let's see if I can make it bigger here. Let's move the vertical asymptote. Do I have another one? I think I have another asymptote here. At -1, am I right? And it's 3. Yep. All right. And as I move the curve, the slope gets steeper and steeper and steeper. And even just with this, I'm already at a slope of 64. And because I cannot get to 3, because 3 would make the denominator 0, I can't get all the way up to a vertical point, but I can go infinitely high. But I can't get to 3 on the x-axis. I can't get to infinity, but that's what it would be. So the slope of a vertical line is infinitely large or infinitely small, depending on which way you're coming. But normally we come from the left to the right. So this would represent a mountain so steep you can't climb it. You can keep rising vertically, but you can't run. The run is not possible because the run is 0. Okay, compute slope and drag. This is the calc definition that slope comes from. Slope introduced in Algebra 1 is rise over run. And we're going to take a detour and we're going to go to vocabulary words and we're going to look for slope. And here's a meaning for slope. This was written back in prior to 2005 when it was posted as a web page. But that's the slope from a basic math point of view. We want secant. Secant function. Secant is what we're looking at now and is used as a term in everyday use for those who speak math. So here we have secant in the New York Times describing the slope of the secant is the 14-day change. One more stop I'd like to take is difference quotient. Difference quotient, when you're in Algebra 1, is the slope. The words difference quotient, difference comes from subtraction, quotient comes from dividing. So in the earliest form, y equals rise over run. Notice it's all verbal, rise over run. Notice no symbols. Notice straight mother tongue. Very easy to comprehend, yet very sophisticated. Rise over run, math class language. Mother tongue. Here we go to symbolic. Then in Algebra 2, we go to function notation rather than y and x notation. Then we go to the difference quotient as used in most calc books, and it's the slope of the secant here, but our toy permits us first to position a point wherever we wish it, and then to drag the curve, the secant, so that it approaches a tangent. So what you have going on is the difference quotient is the slope of the secant, the rise over the run. As h goes to 0, the slope of the secant goes to the slope of the tangent. Here we have it by definition, formally laid out, this time with h. And here's just toys you can play with. You can change your coordinates of A and B and compute the slope, write the equations, and so on. We don't need that one. We can get out of this. You can just throw this away. You don't need it. Get rid of it. Get rid of that. Get rid of that. This is where we are. That's how far we've come. We can take a derivative by taking the limit of the difference quotient. There are a number of spreadsheets. But this is a web page that deals directly with the definition of derivative as the limit of the difference quotient. And if the best you can do is pictorial, if you can't go concrete, then a sequence of pictures is the best you can do. And that's, I believe, better than just one picture. So the best way to introduce is through the concrete or the digital that moves. The second best way is through the pictorial with all your support symbols and notation and all your words, 4 different presentations. Introduce in the most concrete. If you only have pencil and paper, that's the most concrete you get. If you have digital ability, then we can go to a spreadsheet. So let's get out of this one. We'll go back to here. That was the web page. Now we wish to go to the sketchpad that's built for calculus. And I'm going to open that and dump it when you're done with it. So by definition, limit, here's approaching with an analytical point of view. Here's the limit by definition of secant we just looked at. Emojis. I don't think you've ever seen an emoji before because I made them. So here's what they're used for. I just have a plain old ordinary sine curve, a little fancy. And I do have a tangent available to be moved. Let's just play here. I see that the curve is concave down, but the slope is positive. So I'm just going to pick up a slope emoji, and I'm going to say at this point the slope is positive. The slope is, whoops. No, I pick up this one. The slope is still positive here, still positive, still positive. Here the slope is 0. Again, trying to move it. The slope is negative. Trying to move it again. The slope is 0. All right, so what's the other stuff for? Let's back it up again. No, I can't pull the wrong one. That doesn't help. I want this to be at a 0. I think I pulled this one. Go back to here. Now I'd like to look at the concavity. We know, the STEM aware know, and our students are becoming aware that you can look at the function value. If you look at the first derivative, you look at the slope or how the curve is changing. Here, the curve is up because the slope is positive. Now I want to look at how the change is changing. Again, I'm in mother tongue. How the change is changing. Let's drag it. Let's see if I can drag it correctly. Okay, I'm now looking at the second derivative. That's down here. I'm just going to make it bigger so you can focus on the second derivative. As I drag it, the second derivative here is negative. That means all this is concave. Now, here we got positive. All this is positive. So this piece is concave up. We get to about there. And the concavity is 0. The second derivative is 0. That is an inflection point. We move, if I can move it again, let's try it. Now the second derivative is negative. That means concave down. Move it some more. Still concave down, still concave down. All of this is concave down. Let's just throw a few more toys in there. Still concave down. drag it some more. Here we have the concavity changing. We're almost at 0. Still concave down, still concave down, still concave down. We're at 0. It's an inflection point. Moved it wrong again. Now we're concave up. So let's stick in an up. So the emojis permit the viewer to summarize what's going on numerically. At this point, we have an inflection point. The curve is, slope is increasing, it's concave down. Here we have a slope of 0, concavity is down, just toys to play with. Before I do that, I want to play with the point of this page. This is a trace page. I'm reminding you that this is the tangent curve, and as I drag it, it spits out the value of the tangent. So I now have the trace, and what trace does is it traces the path of the derivative. So if I were here, the trace should be giving me a slope of 1. If I'm here, the trace should be giving me a slope of 0. Here it should be giving me a -1. Here it should be giving me a 0. Let's just see if it does that as I trace. This does it for every single point. What it is doing is it's summarizing the derivatives with a new green function, the derivative of the sine. And if your kids know their trig functions, the derivative of the sine is the cosine. Let's take the derivative of that. It's going to be in purple. I turned off the green. I highlighted the purple. I'm going to drag the purple. I want the derivative of the cosine. Well, here the derivative of the cosine is 0. Here the derivative of the cosine is -1. Here the derivative is 0. Here the derivative is 1. Here the derivative is 0. Let's see what we get. So here's the cosine, which is the derivative of the sine. The derivative of the cosine here is 0. The derivative of the cosine here is -1. The derivative of the cosine here is 0. We can do it for the third derivative, which is in orange. And we can do it for the fourth derivative, which is in red. And when we do that, we see the fourth derivative is exactly equal to the sine function. And the memory trick, if you're going to take derivatives, go red, go clockwise. If you're going to take antiderivatives, go blue, go counterclockwise. You're off by a constant, but you got the right function. Another thing one does is use Riemann sums to some areas under the curve. And I have a toy here, and I almost never get it perfect, but I'm attempting to make the box. Well, that's not bad. I did pretty well. Okay, here's the area under the curve. I'm going to hide the boxes, but I'm now going to show the boxes, and you can see clearly now where the boxes are. Notice the height I have used is on the left-hand side. I could have also used the right-hand side. Here I have a picture of the right-hand side. Notice I introduced in the concrete, then I went a little more abstract and just had the picture all ready to go, but there's no movement there. It's static. That's the way it is, but it's better than not having a picture. It's better than just going straight to the computation. This one is, and I think I can move this. No, can I move it this way? No, I'm never going to get it the way I want it. Okay, this is one with, I think, only 8 partitions. Yeah, 8 boxes. And here's a box. So I could go either left hand, or you could go left hand, right hand, or midpoint. And this provides the computation so that you can see that the sums are close but not identical. And with this one, you can change the A and the B. And I think I've got them in reverse order. And you could change the function. Let's just make it plus 2. Brings the whole curve down, and I can get fancy. Here, G is 0. Let's make G 1. No, let's make it even more interesting. Let's make it a line. There it is. Okay, so here, the parabola, we're doing heights. We're doing F minus G. And here, the parabola is always on top. We get positive sums. Here, if I move it a little bit, you see the parabola is on the bottom, the line is on the top. I'm getting negative sums. And this is only with 8 partitions. This one's just laid out to do it, but you can change your A and your B. Let's make this maybe a -2. And let's make this what do I want? Maybe a 19. Now let's make it a 19, a 20. And that'll do the computation. It's only left sum. I'm not worried about it. but it's a different way of formalizing the notation we'll be doing. I think I have a few more to show you. This is where the word cumulative is seen most often. It's a cumulative probability distribution. And there are only, I believe, 32 boxes here. Look at how dense that looks. All that computation I did in pieces. If you need to see it, there's what one piece looks like. That's another piece, and that's the formula that you'll see up here. I can get rid of that. I have a spreadsheet that does the statistics. I'm not even going to bother for that for this talk. I can change sigma, A, and B. Sigma meaning the unit value. So let's just change, for diversity, let's make mu the middle. Let's move that over to 4. Well, let's see if it moves it. There, it moved it to 4. And the standard deviation, let's make that really tighter. Let's make it 0.5. And let's go from A of 4 to a B of 6. There we go. So you can play with the curve. And if we look at the area, it says it's 0.52, and that's how many standard deviations. Well, let's just line it up so that we can do it easily. Let's make it go from 3.5 to 4.5, and I think it rounded it automatically there. Okay, so 3.5 to 4.5 should be within 1 standard deviation. That should give us 34 plus 34 is 68%. So, one more. Maybe 2 more. Okay, here we go with summation versus integral. And then let's go to this one, plots an antiderivative. It does not compute the antiderivative. All it can do is do the sum of the partitions, sum of the Riemann boxes. And here's a line to X. And here's a parabola. And I got the parabola by summing the partitions. Let's change the line a little bit. Let's make it -1, just to change it a little bit. The curve changed a little bit. I still get a parabola. Let's try and change it to a parabola now. All right, now we got a parabola. There's a parabola. Well, I don't see the cubic, so we got to go hunt for it. I see one green dot. Here's a green dot. Do you see any more green dots? Nope, change the function. Let's make it down 30, just so we can see it. Okay, now I can see some of the dots. Here's the parabola. I started here. I'm adding the areas. As I add the areas, you can see the cubic. And there's your fundamental theorems 1 and 2. Get out of this, don't need it, dump it. You could always save it if you wanted to, I don't need to. Okay, algebraic multiplication. This is pre-function, but I'm going to do it anyway. Algebraic multiplication, if all you've got is a visual, this is the summary. To multiply a constant times a binomial, set up a box, place the constant, either way, it doesn't matter, on the edge. So using the tiles, the number 2 is 2 tiles. The number 3 would be 3 tiles. The number x plus 3, or 3 more than a number, would be x plus 3 tiles. That's laying it out. Now fill in the areas. So 1 times x is x, 1 times x is x, 1 times 1 is 1, blah, blah, blah. You could do a multiplication of negatives. You got the idea. I can get out of that. I'm going to a spreadsheet. And I've laid out a multiplication problem. No, I've left it blank, completely blank. So the first thing I'm going to do is create an area. Got the area. What I want is, let's go with maybe x plus 2. And let's go with an x. For the record, I can rotate these any way I want. It's just easier to have them stored that way to start with. Let's make it a 3. I'm going to copy it. I'm going to paste it. I'm going to paste it. No, that wasn't good. And I'm going to get rid of this. I need it a little bigger. Okay, now let's fill in the boxes. I need x times x is an x squared. X times 1. And I need 2 of those. And I need 3. And now I need 1 times 1, I need 6 of these. And the better thing to do is to copy each of them. I have not done that. Final answer. X squared plus 1, 2, 3, 4, 5x plus 6. Okay, that's the pre-function computation. There are more things to use. We're not going into it. You can solve using 2 boxes. There's a whole book on it. Let me just show that to you. Here's the whole book on termtiles, including the masters and including the digital manipulatives. So you can do it concrete or you can do it digital concrete, your choice. I don't need that. We're back to here. We're back to the spreadsheet. I don't need it. Get rid of it. I don't need it. Dump it. You can always download another one. Now I'm choosing to go to the composition of functions, polynomial, rational. Inverse comes later, but I've just picked composition. Here is good. This is the one I believe I want. Okay, 1 function, boring. 2 functions, more interesting. I can edit them. Composition gets good here. I have it laid out for as many as 4 functions. I'm going to make all these 1. Let's leave the x squared. Let's leave the x plus minus 3. So that should give us an x times an x is a cubic. Let's make the green one equal to u of x times v of x, u of x times v of x. We should get a parabola, a cubic. Bingo, here's the cubic. All I did was decide what I wanted the function to be. Now let's just do, let's make it u of v of x. U of v of x. Now we have the line squared gives us hopefully a parabola shifted over 3. Bingo. Okay, that's how you can play with the composite. The polynomial version gives you it all laid out, ready for a multiplication problem. The rational gives it to you laid out for rational function. It's got the top functions, it's got the bottom functions. Gives you some vertical asymptotes. Okay. You can, the point of this was to get you warmed up. Now I'd like to go again to end behavior. This one just looks at the leading term of each polynomial in the rational function, constants a and b, exponents m and n, and we can edit those as we wish. Let's make the top one a higher degree than the bottom. That means the top wins, the bottom is not as big. The top is bigger. It's going to positive infinity. Let's make the bottom bigger. It's going to 0. Let's make them equal. It should be going to 4/5. Bingo, it's going to 4/5. Let's make it go to 2. Eight over 5. No, that's not 2. Try again. There we go. 8 over 4 gives us 2. Here's a summary. For the record, you will find the summary in the end behavior definition in the dictionary. I can get out of that. I can go to the spreadsheet. That's all that's in here. I don't need this anymore. Okay, parent functions. We go to less sophistication now, and this one is not ideal. We're going to, as concretely as possible, translate and reflect. And it does not do this well. This is only digital. This is the best I can do, but boy, it's better than anything I had before. Here's the entire book for exploring functions through the use of manipulatives. Just going to take the detour. There's the cover. That's the table of contents. It includes masters for all of the manipulatives you see here, but I couldn't do it on the screen. I could only do it with an overhead projector and with paper in students' hands. But when the pandemic hit, there was no way to do any of this because you couldn't get the manipulatives to the students. So this was the way one could go. But for years, I couldn't figure out how to do it on the screen. So I came up with this alternative. Let's just look at some of the masters here. Parent functions. There you go. That's the reciprocal. Those are some circles. Let's go back one. We're back to here. I wanted to go to the parent functions, and I think I downloaded it. Okay. The drawbacks. You have to leave everything this scale because otherwise your manipulatives won't work. This is what one uses to drag and move. So, intro tells you all about the original book. Instructions. Here's the instructions. Click on the arrow at the far left to make it blue. Right over here. That's how you select. Click on the green function to select it and make a pink box around it. So I'm going to click on it. I made a pink box around it. Notice it also highlighted use this to drag. So watch me drag. I can put it anywhere I want. translate anything I want. Okay, now that's concave up. I'd really like a concave down. And don't reflect it. You can do it, but don't. The reason I say don't is because you might change the scale. So I'm going to move this to here. I'm going to attempt to select the box. I'm going to copy it with a Control-C. I'm going to take it to my blank and go Control-V. That pasted it. Now I can move that. Okay, you have absolute value functions. You have is greater than or is less than functions. You have is not equal to, so you could make fancy things. You have square roots. Notice you need 4 square roots because you can't reflect with this. In real life, you can. With a digital, with a concrete manipulative, with an exploring functions manipulative, yeah, and all the masters are there, but you can't do it on the screen unless you have an overhead. We have reciprocal functions and some parabolas greater than. We have some absolute values. We have more storage here and here. And that, I think, is 2 to the x. And here's, what's this one? That looks like natural log. If this is e to the x, nope. Didn't pick it up. Can't find it. Okay, let's see if I can drag it. Well, I'm not dragging it correctly. What I was trying to pick up was this one. Now, do I have it? No, turn that off. Now I have it. There we go. Okay. And I threw in asymptotes so it was easier to line up. And let's try and pick up this one. Nope. Turn this one off. Nope, can't get it. Not worth trying. You got the idea. Do I have any more? I have log and reciprocal. And you got the idea. Dump it. Okay, inverse. We start with a vertical line test and a horizontal line test. A square root function is a great one to find an inverse of. This toy does what? Graphically takes the inverse of this square root function. And directions. Oh, constraints. You can't reflect a whole function. You can reflect, you can reflect over a segment. You cannot reflect a graphed function. You can reflect points. So, in order to attempt to reflect this curve, I'm going to first edit the function. I'm going to leave it. Select each point on f of x. And I'm going to pick this one, that one, and that one, and that one, and that one. And I only have those 5. Select the segment on y equals x. In the transform menu, choose mark mirror, transform, mark mirror, and it clicked it, did it. Then choose reflect. Bingo, it did it. Then with the marker tool, attempt to draw in the functions. This I am not good at drawing. That's the best I can do. I think you can see that one is a reflection of the other. I'm going on. Here it lets you put in any function you want. Here you can set your function by parameters rather than typing the whole function. In order to take the inverse of that square root reflected across the line, you'll get that parabola, but only part of it. So the point is you have to restrict the domain. Here is the function in blue. Here is an entire parabola. You don't want that. You only want k the domain of the inverse is now restricted to x is greater than k. So let's see something that will not work. Let's make it k equal to, we could put in -1. So what we should be getting is that parabola, but with too much domain. Bingo. See how it does not? It is not the inverse of the parabola because we did not restrict the domain. So if I make the domain 1, then I should get my mirror image that I want. This is an arc sine, and you can see that the pairing, the function and its inverse point. And you can do it with the arctan. It's too much to look at. I think most calc books will do it, but I'm just going to stick with the arc sine here. I want function and its inverse, the derivative of an inverse function. It is true that the derivative of a function at AB is the reciprocal of the derivative of the arc function at BA. And it is true that the derivative of an arc function at BA is the reciprocal of the derivative of the function at AB. So let's see what I want you to look at. I'm going to drag AB. It drags the mirror image BA. I'm looking at the derivative, the slope of the tangent at AB. Here's the slope of the function at AB. It says the derivative, the slope of the tangent is 0.36. Here we've got this 1 over the slope of the inverse function. and they match. And let's just move A and B. Notice that they match. I don't think I want to do anything with this one. No, it's just yeah, I'll do it anyway. Okay, you can see the tangents intersect each other right there. So what's the point? We're back to the same point, just looked at from a different perspective. I don't think anybody else can do that with inverse functions. Okay, sine, normal sine curve. Everybody does this. Everybody does this. Spreadsheets often open up by themselves, whereas the supposer, you have to download it and then open it. Okay, we want plain old ordinary sine curve. You can adjust A, B, C, and D. Let's just prove it to you by making this 2. Shoves it up 2. Bingo. Tangent, sine, sine. This is the one I use the most often. The top function is blue, the bottom function is pink. Let's make them the same. And now we get one right on top of the other. Let's go a shift. Let's make this 1. Now let's make it 0.5. Shifts it up. No big deal. You can download Geometry Sketchpad. What else should I show you? Get rid of that. Back down to here. Languages of the math class, free Sketchpad, spreadsheets, digital manipulatives. Those are the algebra tiles. We looked at those before. The PDF of this page is there. The video is not. I have not written it yet. I think we're almost done. Get out of there. This is the talk. I hope you got something out of it. Have a lovely day.